organizing parallel computation, which is tree based, and another that we had started on, which is partitioning into smaller problems and then solving those independently. And so this is the example that we are going to start with. Tell me something. Tree based, how? So give me one. There are many ways of doing it.
Means mine is quite inefficient in the sense that work is n log n and time is log n. So what I do is that processor knows, it takes one node, so it knows that I am I position in array A, and in log n I can calculate my position related to in array B, how many elements are smaller than me, and then I know the final position in the final.
Okay.
Log n time and n log n.
All right. So we are going to determine every element's rank in the final position. Right. I know my rank. What's a rank? The number of elements that are less than me. Right. So if I am the first element, my rank is 0. If I am the 10th element, my rank is 9. So 9 elements are less than me. And so I know the rank. If I am in A, I know my rank in A. I just need to find out my rank in B. Right. If there are 13 elements that are smaller than me in A and 16 that are smaller than me in B, then there are 29 elements smaller than me. Right? So I'm the 30th in the final array. And so how do I find my rank in B? It is sorted, binary search, find it. Okay. So eventually my rank in the union is my rank in my array, which I already know, plus my rank in the other array, which I need to compute. Each element can compute it in log n time. There are n elements. And so in n log n work, n log n time.
Log n time work.
Log n time for each.
Sorry? Log n time and n log n work, we will be able to compute the entire merge list. Right? So once I know my rank, how do I create the merge list? Just put it, right? My rank is 13th, then I put myself in the 13th position. Does it require concurrent read, concurrent write? What does it need? Concurrent read would be needed because all these different elements are doing log search at the same time. But concurrent write is not needed. Right? Once I know my position is different from everybody else's position. If things are not unique, what do you have to? What do you do?
Priority.
Priority what? But if they came to the same rank, then concurrent write would be needed. They both would want to say.
Okay, just check whether there is an element. We can check. Means we can say that
if the elements are not unique, the rank in one of the array will anyway be different. So it will be different.
One of the array will be different meaning?
For example, if there is a sorted sequence of numbers, if a number comes 2 times, then its rank in A will be different. Its rank coming out in B will, the numbers which are smaller than it in B will be the same, but its rank in A will be different. So final position.
So what we can do is that we can say that.
Is that enough? How do you compute your rank in the other element? So if there are multiple things that are equal to you, then where do you find your position?
That will be deterministic element for
the one is lesser than me. So even if they are.
So if they are equal, then you don't count them.
So one of them can move to the less than or equal to one of them.
The point we have been finding.
No, one of them, that's the thing, right? You can't do one of them without concurrent. Right.
So during initial search, one does a search on which how many elements are less than me. The other array does a search for how many elements are less than or equal to me in the other.
No. I've got multiple copies of 39 in array A as well as in array B. Right? So a given 39 in array A must come to its rank in array B. Right? And a given other 39 must also come to its rank in array B. How do you figure out their respective ranks? Do they count the 39s in array B or they don't?
So the algorithm binary search is deterministic, so they will all come to the same position. So the final thing, because the ranks in original array is different, so they will map to different positions.
Okay. Now that leaves what happens to the 39s in the other array, right? How do you make sure that they come to ranks greater?
So we can search for the end of the element 39 in array. So that all those positions are skipped.
Make it linear.
Linear.
Make it linear.
No, use just search for the end of that element.
Okay, so that's an interesting thing to think about. I'll leave you to think about, and do think about it. Let's talk about the basic case right now, and there are various ways in which
all the copies of A and B in the resultant version.
you would want it, right? Yes. Right.
So we can do like one binary search which gives the first occurrence and one which gives the last occurrence. That can be used to like
And once the 139.
Yeah, they're all in the right direction. Think about it. Let's not discuss that in class. Let's talk about how to make it better. So the log n and log n is correct. You can find these ranks quite efficiently by binary search in log n time and in log n work. Okay. Can we do better? That was the question.
Split it in like take the first sequence, take the first element of first sequence, last element of first sequence, find the mid element, find the rank. So basically, find what would the rank of that particular element be. Basically, split the two sequences about that element, which can be done in order log n for both. So you got two sets of two sequences, and you can do this recursively, and those can basically.
If you do this, then you're again following some kind of a binary tree pattern, which will take you log n time.
Yeah.
Right? So we want to improve. Currently, our work is bad. We would want it to be as good as order n. In sequential, we can do it in order n time.
So the work in that case would be less than n log n. I think.
Maybe, not clear. And the time we have is log n. Maybe it's okay. Maybe we can do better. Okay. So if you were trying to do better, what would you do?
So I would mean, like if I form some form of tree and each process takes order one time, so I can have work as n and time would still be log n.
I am not sure how.
can get some kind of n plus log n.
So basically, we have to.
Why is it taking that much time?
Making
Sorry, that much work. Let's target work first. Sorry?
Doing useless comparisons.
Lots of useless comparisons, right? We know a lot about. So we have taken these n things and independently we are doing log n search on it. We know their relative positions.
Partitions are also sorted with respect.
They're with respect to each other, right? So we aren't using it. So there are lots of comparisons that we already knew of, and we're not. If a given element is found at third position in the other array, then element to the right of it cannot be found in the second position.
Maintain the position of
Right?
the
It has to be found after the third position. Okay. So let's try this. Suppose we partition it into blocks. Okay. And although it says log n size blocks, we'll figure out what is a good size. And we are going to choose from one of those arrays, let's say B, one element in each of these blocks. So log nth element, you can start with the first also. Boundary condition doesn't matter. Start with the first also. Log nth element, 2 log nth element, 3 log nth element, all the way up to the other end. Okay. So now I've got n by log n elements of B that I have chosen. If I only were to try to rank these elements in A, how long would it take? Just the same algorithm as before. Instead of n elements to rank, I only have n over log n elements to rank.
Log n of the order and then.
So log of this, right? Time is log of this, isn't it?
Time is log of size of A.
Time is log of size of A, sorry. Time is log n, correct? And the work is?
N by log n into log n, which is order n.
Exactly. N by log n times log of n by log n, right? No, sorry, log n is the other side. N by log n times log of n, and the work has come down to order n. But we aren't done yet, right? What remains to be done? We have found for every sample in B where it should be found in A. What about the elements between the samples? They'll be found between those respective spots where you found those, let's call them pivots or samples, right? So elements between samples will be found between the samples locations where samples were found. Okay. How many positions there may be? There are how many elements between samples, first of all? Log n, right? So there are log n things that, approximately log n things that we don't know the rank of. So we need to find their rank. But how many elements of the other array A may there be in which I need to find the rank of each of them? Let's look at this picture. Okay, I've got A and B, and I've taken, so in this case the upper one is B based on the description that I had. Lower one is A. I've taken every log nth element in B, located them somewhere in A, right? Only thing I know is that they are not going to cross. If somebody is located at location A, location P, then everybody to its right will be located to its right of P. Okay, but it can be anywhere. And for example, if I wanted to figure out where the elements in the blue in the top will go, they'll go somewhere between those two locations. Okay. Similarly, elements between, oh, that's not colored. The second or the third block from the right of the top, elements there will be anywhere in this bigger than log n size. So if we were to do binary search, then we would take the log of the size of this, which is not log n necessarily.
Can be n minus 1.
It can be as bad as n minus log n, right? All of them are to the beginning, and then there is one chunk left. All of them is in the remaining.
So the total work will be still with, if we increase one work, the other work is decreases.
Other work meaning the first phase?
If I increasing the size of one such block, then the other blocks are shrinking, so the total work is still probably. Time is the maximum of all those.
So if you're going to take approximately n things, right? Because n over log n things, or only log n elements of B we know the rank of. Remaining n minus log n we don't know the rank of. So that many ranks need to be found. Okay, and some of them may take a long time. Some of them may not. What is the longest that anybody could take?
Order log n minus 1. Order log n.
Order log n, right? Because this other big array can be as big as n. Okay. How many of them can there be? Are you sure?
How many can? How is the log n?
How many of them from B, the blocks of B, would have big things to merge with? Why order log n?
So big as in what? Big as in log n of order.
So we're trying to figure out the work, right? The time is log n. Right? Assuming that I have enough processors that every element can be done independently, then the worst case time to look for in the big array A or one of the big blocks of A is log n. Right? But if you did that, how much work would you be doing? You will be doing log n work.
Log n plus.
There are approximately n things
Log n plus n.
whose, if there are enough number, if half of them are going to have big chunk, to be in a big chunk, then it's n log n.
There will be only constant number of big chunks in possible. As in if the big is order n size chunk, there will be only constant number of big size chunks.
I said, suppose all the pivots happen to go to the beginning, right?
Then only one will have.
Then one will, right? Suppose half the pivots go to the beginning. Right? The remaining are distributed equally. But what you can say for sure is that if you take this big block that you have found, it can also be broken into sizes of log n. If we know where these elements are in the other block, in block B, then what are we guaranteeing?
We need to certainly know.
All the pivots between this big block are going to the same block, right? Which is at most log n in size, right? So now there are, when you try to find elements of a block here and find their rank in here, and you discover that this is too big, then you say, let's instead find them in this block. Okay? And as a result of which, now those two blocks will be found in two sections of the same block. And so total time will be log n, and total work will be order n. Okay, you can do sequential merge at this time because there's only log n things to merge. Okay, and by log n different things, and each merge size is order log n. Now, can you do better? Where can you do better? Only in time, correct? Because you couldn't possibly do better than order n work, otherwise you have a sequential sublinear merging algorithm. So where are we spending time to do this search? Right? That's where the log n time is being spent. Can we search through a smaller section maybe? Do we actually want to search through the whole thing? or can we search among a sample of the other array?
Choose log n samples, make another array.
Something of that sort. Okay, so we don't really, because it's taking too long to search through this entire second array, we'll search through some of them. And hopefully then remaining elements, final rank still needs to be found, and that can be done fast enough. So we can expect better. So let's do this. We're going to break, instead of log n blocks, we're going to break it into root n blocks. If you just did the previous algorithm with instead of log n root n, what would you have got? Log n, just take root n blocks and root n samples, pivots. Take root n elements, every root nth element now, right? And we're going to rank it in B, sorry, in A, because we're taking it from B. How can we speed up that search? And reason for root n will become clear when you think about how can we speed up that search.
I have root n blocks, so I can select which block means to actually search from.
Root n elements that root n searches we have to make, right? So we have less searches to make now. In the first case, we were making n by log n searches. Now we have reduced the number of searches that we are making, which kind of means that we can assign more processors per search, hopefully. If we had n processors, we could assign root n processors per search. So if I had root n processors and I wanted to find one thing in an array of size n, what does the binary search, or the variant of parallel binary search where I'm using P processors, tell us? How fast can we do it? Log n to the base root n, right? Which is constant time. So we are spending enough processors to speed up the time, because we have done the work. We have brought it to order n. We're trying to get the search time down. So we said search was taking too long. Let's devote more processors to the search. But if I had n by log n things, then it would probably be too much work. But if I had only root n things, then with n processors, I can, in constant time, figure out where this element is. Okay, and there are root n searches to make. I'm going to allocate root n processors to each of those searches. So n processors in order 1 time will have found all the pivots. Okay, in constant time. Now, what remains to be done? We'll probably similarly do from the other side also. We're basically going along the same path. Did we end up spending too much work here? How much work was done in this step? There are n processors. You did it in constant amount of time. Couldn't have done more than order n work, right? So far, time is great. Work is good. Great. But there is work to be done still. Suppose we recursively merge those pairs. We have root n block here, root n block here. We merge two things of root n, and we have root n such merges to do. And so we can say the total time is order 1 plus time taken to process root n, right? Which is log n. Still not order 1 because there's enough work remaining to be done. The work will be n log n. Because although you did order n work, there is enough times you have to do order n work that it adds up to greater than linear. So we've made it faster. Right? Log n is practically constant for all practical purposes. But the work has gone up slightly. Still n log n time you can imagine being almost linear. So far we are talking about partitioning. Right? I'm going to delve into another technique where you combine two different algorithms. One which is fast but ends up doing too much work. One that is work efficient, is not as fast. And you combine it to get something that is fast as well as work efficient. That's a different technique. Okay. Let me stop at this point and think about how you would combine. We have two algorithms now. One which is root n based, which is really fast, not perfectly work optimal, still reasonable, but not perfectly work optimal. The other one is work optimal, but not as fast. Okay, so can we combine these two somehow to get the best of both worlds? So we'll stop here. Okay, we'll stop here. Let's begin. So what we are going to try to do is don't use the fast but suboptimal algorithm on the entire data set. Okay? Use it on small pieces of data in a way that it doesn't add up to greater than the optimal work. Okay? So we're going to make data sizes really small, log n. So we're going to divide A and B into sizes log n, right? And sample these. How many are we going to get in the A prime and B prime sequences, which are the samples? N over log n. So now, instead of a problem of size n, we have a problem of size n over log n. Can we take that and solve it using the fast but less than optimal algorithm? If we had n over log n elements to merge, how much work would it do? Order n, right? And we wouldn't be done yet though, but because our blocks were so small, there will be very little work left to be done. Right? Because we made blocks only log n size. And so in this case, this approach works because we were not that far away from optimal. Okay, so let's look at what would happen. So we have A and B. We have sampled it every log n now. So just because I had to fit log n into a small space, I'm calling it LLG. So wherever you see LLG, it is log. Okay, log n. And so each size is log n, and there are n over log n of these. We're going to take every element in this block and make new sequence A prime and B prime, and merge these using the fast but suboptimal algorithm. What remains to be done? We can merge sequences from there and here, right? Is there too much left to be done? So let's look at one of these elements. We have found one of the samples of B among the samples of A, right? We haven't looked for